Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today we'll take a quick look at RC filters by way of a series of illustrated example problems. This lecture operates under the presumption the viewer has a basic understanding of RC filters and can calculate gain expressed in units of decibels as illustrated in the RC filters lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only didn't recall its contents, please take the time to do so now. Mastery of RC filters necessitates active participation on your part. As such, I'm asking you to please pause the lecture when asked to do so and attempt the example problems on your own. If your answers don't match those illustrated, feel free to rewind the lecture and correct any mistakes you may have made. Consider the following series circuit consisting of a 200 ohm resistor and a 0.4 microfarad capacitor. The source, Vin, has an effective value of 30 volts and an excitation frequency that can be varied from 1 to 20 kilohertz. Is this a high-pass or a low-pass filter? Note Vout, the property of interest, is being read across the resistor. If you're tracking, you should realize that this is a high-pass filter. Given the capacitor's impedance is frequency dependent, we should observe a large voltage drop across the capacitor at low frequencies, leaving very little left over for the resistor. Conversely, we should observe a small voltage drop across the capacitor at high frequency, leaving more left over for the resistor. In summary, at low frequencies, Vout will be low, and at high frequencies, Vout will be high. This fits the description of a high-pass filter quite nicely. Let's see if this is the case. Second question, what's the critical frequency for this circuit? By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. The critical frequency represents an occasion in which the magnitude of ZR equals the magnitude of ZC. F of C, the critical frequency, equals 1 over 2 pi RC. Substituting in our given values, we find FC to be equal to approximately 1989.4 Hz, super close to 2 kHz. Next, see if you can determine the output voltage at the critical frequency. Once you've got this property, normalize the output and see if you can express a gain figure in units of decibels. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. At the critical frequency, the complex impedance of the capacitor will be 200 ohms at an angle of negative 90 degrees. The complex impedance of the 200 ohm resistor is 200 ohms at an angle of 0 degrees. As we anticipated, the capacitor and resistor do indeed present impedances of equal magnitude at the critical frequency. Let's now examine output voltage for this high-pass filter circuit at the critical frequency. Perhaps the easiest method of solving for voltage across the resistor is through the use of the AC voltage divider rule. The AC voltage divider rule, set up to solve for Vout, demonstrates that Vout will be 21.2 volts at an angle of 45 degrees. You'll note output voltage at the critical frequency is source voltage divided by square root 2 and is phase shifted from it by 45 degrees. This is an identifiable feature of filter circuits at the critical frequency. If we wish to normalize this output, we would have to divide output voltage magnitude by input voltage magnitude. Doing so leaves us with a dimensionless constant 0.707 or 1 over square root 2, meaning output voltage is roughly 70.7% of input at the critical frequency. Finally, gain in units of decibels equals 20 log of voltage output divided by voltage input. Substituting in our given values, we find this to be a gain of roughly negative 3 decibels. You recall a gain of negative 3 decibels is synonymous for a condition of half power. This makes perfect sense. At the critical frequency, one would expect this circuit to experience half power. Moving on, let's now see if you can determine these same properties at 500 Hz, roughly a quarter of the critical frequency, and at 8 kHz, roughly 4 times the critical frequency. You should observe some very predictable behavior illustrative of a high-pass filter operation at regions below and above the critical frequency. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. At the reduced excitation frequency of 500 Hz, the complex impedance of the capacitor will be roughly 795.8 ohms at an angle of negative 90 degrees. Capacitive impedance goes up. The complex impedance of the 200 ohm resistor remains 200 ohms at an angle of 0 degrees. Given this change in impedance, we should expect more voltage to be dropped across the higher impedance capacitor and less across the lower impedance resistor. This makes perfect sense for a high-pass filter operating at a frequency lower than the critical frequency. The AC voltage divider rule demonstrates that Vout will be roughly 7.3 volts at an angle of 75.9 degrees. You know, output voltage at 500 Hz is less than that experienced at the critical frequency. This is an identifiable feature of high-pass filter circuits. If we wish to normalize this output, we'd have to divide output voltage magnitude by input voltage magnitude. Doing so leaves us with a dimensionless constant 0.244, meaning output voltage is roughly 24.4% of input. Finally, gain in units of decibels equals 20 log of V out over V in. Substituting our given values, we find this to be a gain of roughly negative 12.3 decibels, meaning this circuit is experiencing less than half power. This makes perfect sense. At frequencies below the critical frequency, one would expect the circuit to experience less than half power. Let's do the same thing for the increased excitation frequency of 8 kHz. At the increased excitation frequency of 8 kHz, the complex impedance of the capacitor will be roughly 49.7 ohms at an angle of negative 90 degrees. Capacitive impedance went down. The complex impedance of the 200 ohm resistor remains 200 ohms at an angle of 0 degrees. Given this change in impedance values, we should expect less voltage to be dropped across the lower impedance capacitor and more across the higher impedance resistor. This makes perfect sense for a high-pass filter operating at a frequency higher than the critical frequency. The AC voltage divider rule demonstrates that Vout will be approximately 29.1 volts at an angle of 14 degrees. You note the output voltage at 8 kHz is more than that experienced at the critical frequency. This is an identifiable feature of high-pass filter circuits. If we wish to normalize this output, we would divide output voltage magnitude by input voltage magnitude. Doing so leaves us with a dimensionless constant of 0.970, meaning output voltage is roughly 97% of input. Finally, gain in units of decibels equals 20 log of V out over V in. Substituting our given values, we find this to be a gain of roughly negative 0.3 decibels. This makes perfect sense. At frequencies above the critical frequency, one would expect this high-pass filter circuit to experience more than half power. That's about it. Really, the only thing more I could ask you would be to plot these results for a range of frequencies, but ain't nobody got time for that. Computer, do a frequency sweep and plot output voltage on a semi-log plot. Doing so yields a plot like this. You'll note output voltage is plotted linear on the vertical Y scale, and frequency is plotted logarithmically, where each equal interval represents a power of 10. At low frequencies, output voltage is low, and at high frequencies, output voltage is high. There's an identifiable knee or corner at the critical frequency, after which output kind of levels off. A plot of normalized output looks almost indistinguishable, only the vertical axis now represents the dimensionless constant of V out over V in. Finally, a plot of gain in units of decibels looks a little snappier, in that the upward slope seems to be almost linear, and the knee or corner at the critical frequency is a little sharper. In fact, this plot is so sharp we can do a little straight line approximation. From 1/10 the critical frequency to the critical frequency, we can assume a slope of negative 20 decibels to 0 decibels, after which at the critical frequency to 10 times and beyond the critical frequency, the approximation assumes a 0 decibel flatline. We know this isn't true, however it's a great approximation tool, especially at frequencies less than 1/10 the critical frequency and greater than 10 times the critical frequency, i.e. regions in which the difference between the actual gain and the linear approximations aren't so distant. You note at frequencies much lower than 1/10 the critical frequency, this high-pass filter exhibits extremely low gain. For example, consider the roughly negative 40 decibel gain exhibited at 1/100th the critical frequency at roughly 20 Hz, and the roughly negative 60 decibel gain exhibited at 1/1000th the critical frequency at roughly 2 Hz. In fact, for frequencies beyond 1/10 the critical frequency, i.e. less than about 200 Hz for this particular example, there's a shortcut means of calculating gain given the small difference between the straight line approximation and the actual response. The shortcut method doesn't necessitate circuit analysis, but rather a simple formula which states gain in units of decibels will be equal to positive 20 times the common log of the frequency of interest over the critical frequency. Note we're using a positive sign in front of the 20 because we're dealing with a positive or rising slope of a high-pass filter. For example, let's say we wish to know the gain at 50 Hz. This is obviously much lower than the critical frequency and deep inside the stop band for this high-pass filter, so we're totally safe to use the shortcut formula. Substituting in our given values of 50 Hz and 1989.4 Hz yields a gain of roughly negative 32 decibels, which kind of confirms what we're seeing on this graph. If we're ever asked to quickly approximate this filter's gain at regions beyond 10 times the critical frequency, we're safe to assume it has a 0 decibel gain. Alright, that wasn't too hard, was it?